Yeah, it's coming up. Okay, so, well, it's not quite Halloween, but it's almost Thanksgiving too. All right, so it's week 9, lecture 18. We finished up the title chapter. So as you can see here, that it will be open in about an hour and 15 minutes, and it'll close on Monday. So go ahead and knock that guy out, please. We'll hit the syllabus here. Here's the syllabus. Just want to keep everyone on the same page. So summary 3 is due. Are summary 3 submitted at all taken care of? Okay, great. I think a lot of times with 102 it goes faster than 101. Everyone's got a little exposure to Excel. Exam 3 will be launched, and then our next thing is problem set 2. So I thought we'd just, take a look at problem set 2, and if we get a chance, I'll launch you out into summary 4. So let's just go take a look at problem set 2, see what any stumbling blocks might be there. Sometimes there's a typo or two that I need to take a look at. Did I blow right past it? Tell me when. Okay, good. Problem set 2, nice. Okay, so all 5 problems are similar to those covered in the text or class. All required data is given or is found in your text. Remember to show all calculations, terms, and units, and organize well, unless otherwise specified. Well, there's a typo right there. Otherwise, just one word. Call me on that. Or I can blame Mark Olson. It's okay, either way. Give answers to 3 significant digits. No need to submit as PDF. Excel, Word, or scan are also okay. All right. Nice. Okay, so box 4.1 of your text gives 2009 data comparing the world's land biomass storage rate to the world's energy consumption. This is a good one because Shramsky does something similar. We can compare what Everett says with Shramsky. Yeah, the world's primary energy consumption is what percentage of the world's unused annual land biomass storage rate. Okay, well, that's a good problem. Some big numbers. So box 4.1, let's scroll back to that.
That's on 119.
119? Okay. Oh yeah, I actually have used this box before in some of my papers. The world's primary energy consumption. It's, here I'm going to make a disclaimer. I'm going to make a disclaimer that what I'm about to show is not necessarily the answer to the problem. I'm just going to help you think through it, okay? I mean, there's a chance I will make an error, so don't say, oh, I did it. This is the problem all the time in teaching, is that, yeah, and we're not always right. I'm just sort of helping you through the thought process and how to read the thing. So, it was the same, it's the same thing with people, people come up to me in the practice, how do I build this? Well, I'm not going to tell you how to build this because then it's my project and then I become liable if it doesn't work. I'll help you just think through the problem. So you're sort of open, and I may or may not make a mistake, but I'll I promise to do my best. How about that?
That works for me.
Yeah. Okay, so I'll put this down here. I'll put this up here so I can see it. So, so the world global primary energy consumption. So I'm just going to put energy per year equals 500. Well, it's 502. Since the problem does ask for 3 significant digits, let's work with 3. So 502 exajoules. That's total, and I just like to start with that number because that's, where we start with the very, with lecture 1, 502 exajoules per year. Yep, exactly. Okay, the world's primary energy consumption, and that's what we've just written down. Rate of global primary energy consumption, 502 exajoules per year. There we go. Now what we want to do is compare that to the unused annual land biomass storage rate. And I want to bring this up quickly and show that we actually have covered this to some extent with Schramsky. Here's Schramsky. So he's got these things measured in zetajoules. 1 zetajoule is 1,000 exajoule. Okay, so 2 zetajoules is the energy flow due to the net annual primary production of the planet. So that's where we get more or less this thing. So this is kind of straight out of Schramsky saying that the planet makes 2 zetajoules or 2,000 exajoules of biomass per year. Humanity consumes a quarter of it. So if I were just to take a stab in the dark, I would say, so that means that 1,500 exajoules go unused. It's the 3 blocks on the top there. So you could look at it and say, well, we use 500. So let's go back to the question. The world's primary energy consumption rate is what percentage of the world? So I would say, well, 500 is 1/3 of 1,500 or 33%. So I'm just going to throw that out there as a, well, it's a tricky one because, if you go back here, well, this block here this block right here represents all of the primary energy. Coal, oil, gas, nuclear, geothermal, you name it. And it's going to be a little more subtle, but I'm just going to, guess off the top of my head, I would say, well, this stuff is getting unused. I know it's going to be more than that, but let's just say if all of our energy came from primary biomass right now, this bottom block would be the used portion. These top 3 would be the unused portion, so it would be 1/3. I mean, obviously, that's not the case, but I'm just going to, again, it's kind of good to start with, initial guess equals 1/3. But let's dig a little bit deeper into box 4.1 and reread the problem. And what percentage of the world's unused annual biomass storage rate? So it's, first of all, listed in tons. And we can also see that energy stored in bio equals 25,000 exajoules, and that's total, that's not per year. The net annual production biomass energy consumption. This is not an easy problem here. Rate of energy storage by land biomass. There we go. Okay. So I'm going to write it like this. E dot. So the E dot is the rate of storage of bio equals, and this is the first line in the second half of the table, and it says 2,400 exajoules per year. Okay. And now it also says that there's a biomass energy consumption rate So I'll write it like this. And the dot over it means this is the consumption rate, so rate at which we're consuming. So the energy consumed, so S for storage, C for consumed, bio, equals 50 exajoules per year. So that's your wood, your purpose-grown crops, algae, what have you, for biomass energy consumption. So again, this is just my own thought process in reading the problem through. I'm going to, well, you might also take that 29 and you can add it to that. Let's just do that for the sake of completeness. So E dot consumed, or bio food, equals 29 exajoules per year. So now this total is 79 exajoules per year. Now, so this is telling me that the planet is storing 2,400 and we're only using 80. So what I'm going to do is see, what's left over, because that's what the problem is asking. What percentage of the world's unused annual? So let's just go ahead and say, so E dot U for unused, bio, equals 2,400 minus 79 equals, pop that in, 2,400 minus 79 equals 2321. Now, so I look at this. This is exajoules per year, 2321. I come up here and look at our rate, 502, and let's just do that as a percentage. So percentage extra, if you will, equals 502 divided by 2321 equals so I'll just do 1 over x on that times 502 502 equals 21.6%. All right, now, that number almost jives with the Shramsky. It's pretty close. Now, these numbers, this book was written first in 1996, then published in 2012. Shramsky was written in 2015. So when Shramsky was written, I can only assume, in fact, well, let's see what Shramsky says in terms of our energy consumption, because if it's higher than 502, then you can see how that would be greater than 21%. Let's just take a look. And this is
I think he used 504.
504, really? Okay, good
Maybe,
memory.
don't hold me.
Yeah, okay. Sorry, I already quoted you. Here's Shramsky. I can do a quick search. Let's see if we can find 50.
You're looking at me,
Do you think I saw it there? You think you saw it?
Yeah. I can make this maybe. The living file completed, I thought was there.
Oh, here we go. Oh, hang on. This says 5.3 zetajoules per year.
It'd be 530.
That'd be 530.
That's a lot larger.
That's significantly larger. That's why I didn't see the 50, because he's written it out in zetajoules. And in some cases, they're doing a joules per person and multiplying it by the population. In some ways, they're just like trying to track how much primary energy was sucked out of the ground, the various fossil fuels. So anyway, there's a little bit of discrepancy, but, and I think we've solved this to the point now where it's going to be something in that ballpark. And that's really the point, that you've sort of looked through this thing and thought through it. I don't know if that is the exact answer, but that's one way to go about thinking about this problem. Okay, let's see what else we got here. That's nice that we can take the textbook and a paper that we've read, do a little research, and corroborate. Yeah. Okay, so here's your friends with the 500-gallon hot tub. Water temperature's 45. Campfire boiling. Oh. Okay, so box 4.8. Let's head out over to box 4.8. That's on page 147. And we're going to use the specific heat equation. Yeah. Campfire. So we're looking at wood. we don't even need to know how much wood. We're just looking at energy in megajoules. So let's take a look at that. So the equation we're going to use is Q equals Cp M, M delta T. So in this case, and I'm just gonna kind of run through this in sort of a fast engineering format, if you don't mind. So I'm just gonna look right in the book and see that C sub P is the specific heat of water, and we're looking at 4,200 joules per kilogram per Kelvin. Let's go ahead and write that out. 4,200 joules per kilogram per Kelvin. Now the mass, I'm just going to go ahead and write in 500 gallons because that's the best I can do on the mass for now. So 500 gallons. And now I'm going to convert gallons to liters. It's 3.8, but I want to use 3 significant digits. So let's use the 3 sig digs. Gallons to liters. let's go with 3.79 on that one. Let's do it this way. 3.79 liters per 1 gallon. There we go. And then I actually need the mass because I've got kilograms down here. So I'm going to put 1 kilogram per 1 liter. Now, if we want to get a little bit technical, let's look at the density of water as a function of temperature, because as the water heats, it's going to become less dense. But let's at least get an idea of how far off we are. So density, water as function of temperature. I think pretty soon Google's just going to read your mind and just tell you the answer before you even think of it. It's getting close, isn't it? Yeah. Well, there's my buddy Izzy Goldwasser's brain massager too. It's just a slippery slope. I kind of want a table. I don't want to have to. Density of water. Let's see what these guys have to see. Colby College, what do you have? What do you have, Colby? Handbook of Hydrology. This is fun, okay. This must be for some solvent. I don't know what that is. Table, degrees, row. It used to be that nice CRC. No, I don't want to go with that one. Sorry, guys. Let's see. I want the way. I just want to see numbers. Density. PDF, let's see what these guys have. SUNY. We got SUNY. Allow and remember. Okay. All right. So this is in Celsius. We know we're going to get up to about 100 C. And we only have one table here. Yeah. So the density is I didn't realize it was quite this, I thought it was a lot closer to 1 at much higher temperatures. And in fact, it looks like it's never really exactly 1. What is interesting to note on this chart is that water is most dense right around 4 degrees Celsius. And we're up to like 9.95, et cetera, over 20, at 29. That's about room temperature. So, we could for this problem say the density is 0.996. And in fact, since we've gone to this trouble, let's just do it. Give ourselves some math to do. 0.996, so let's just go ahead and pop that in. 0.996 kilograms per liter. Okay, so already we can see our gallons are canceling, our liters are canceling. We got joules, our kilograms will cancel. Now we just need to do the delta T. Now in the problem, we're going from 45 to 212. Exactly. So we're going to do that. So, so we're going to do 212 minus 45. Now we know that a degree Fahrenheit is 9/5 of a degree Kelvin. So we'll multiply by 5, we'll divide by 9, and this is, I'll just sneak a little F in there, and this is going to be 9 degrees Fahrenheit is 1 degree Kelvin. Okay, so the Fahrenheits will cancel, the Kelvins are going to cancel, and we'll end up with joules. So that, again, I just kind of, well, I guess I didn't rush through it that much, but I put the whole problem on one line. It's kind of an efficient way of doing it. Now, let's go into, I'm going to do this in Microsoft Excel. With that many numbers, it's just too easy to make a mistake. Okay, so. And this is good practice for 213, so bear with me. So C sub P, and I'm going to put this in, I'm going to put the units in joules per kilogram per Kelvin, close parens. I'm going to put the mass in, I'm actually going to, this is not, well, no, I'll put the volume. This is going to be the volume in gallons. I'm going to put in the gallons per liter. I'm going to put in density, and this is going to be in kilograms per liter. I know I need that. I'm going to put in delta T. This is going to be in Fahrenheit, and I'm going to do F. I'm going to do kelvins per F. I'm also going to make this a little bit bigger so it's not impossible to read. So we can take this, I'll take that, I'll do a control-1, turn that guy into a subscript. There we go. And we've got 4,200. And we're going to make that yellow as an entry. 500 is also an entry. That's going to be yellow. Gallons per liter, we put in at 3.79. 3.79. And I'm going to throw this in. I like to put those constants in as blue. It's a little bit smaller. The density, I put a R in for rho. I'm going to go ahead and change that to symbol. SYMBOL. And what we're going to use, we're going to use 0.996, so 0.996. That's also a constant, so that can be blue. Delta T, let me turn that delta into a symbol also. There we go. Equals 212 minus 45. And we know that kelvins to Fahrenheit are 5/9 equals 5 divided by 9. That is also a blue constant. I'm going to put it at 3 significant digits just to be consistent. Delta T, that's yellow because that was given. Okay.
What did you do for the Kelvin per Fahrenheit?
Kelvin per Fahrenheit, so I just said equals 5/9.
Okay.
Yeah, so 5 degrees Kelvin is the same as 9 degrees Fahrenheit. And I think I have everything. So now I've got my Excel set up, and now I'm going to do, this is basically dQ in joules. SYMBOL, symbol dQ in joules. So I know that this is in joules per kilogram Kelvin. I'm just keeping track of my units right now. Gallons, gallons per liter, kilograms per liter. That's nice that density is in kilograms per liter because my specific heat is also in kilograms. There's delta T, here's K per F. Okay, so now it should just be equals 4,200 times, and now I'm just looking to my sheet over here and just running right down the list, times 500 times 3.9 times density times 167, which is delta T, times 5/9. Okay, so everything was just multiplied together. There's another function there where I could have used product, but as it turns out, there were no. I mean, the only number in the denominator was the number 9, but I rolled that into a single coefficient. All right, dQ, that is in joules, kind of a big number. Let's convert that to number format, comma, equals, okay. There's joules, copy, paste. Now I've got it in megajoules. Equals that divided by 1E6, dink. Control 1, number. I only need 3 sig digs, so there you go. So the hot tub left unattended, started to boil, and you determined that there were 735 megajoules pumped into it. Now, the energy content of wood is well, it varies. Let's just take a peek out online. it's gonna be different for, pounds per cubic feet, pounds per cord. Yes, they don't want to give it to you in megajoules per kilogram. I want the easy numbers. I want megajoules per kilogram.
The heat value of air dry wood,
Yeah,
15 megajoules per kilogram.
15 megajoules per kilogram? Okay, thank you.
1,000 phosphorus on 8.
Oh, super, okay. That's a reasonable estimate, yeah, I can remember that now when you say it. So 15 megajoules per kilogram. So you might say, gosh, that's a heck of a lot of wood, or, a heck of a lot of energy. The number we came up with, 735 megajoules. We can see how many kilograms of wood that would be. So let's just go back to our simple calculator. Well, actually, no, let's do it in Microsoft Excel. E wood. This is going to be some megajoules per kilogram. 15. Now M wood, this is going to be in kilograms, just equals that number divided by that number. Okay. So these guys had a pretty good fire going to get that thing boiling. 49 kilograms, 100 pounds of wood. So anyway, it's a pretty good problem. And let me put I'll put this as a subscript too.
Did you just divide the two? Is that what you did?
Yeah, I just divided the total energy by the energy density, and that gives me the total mass. Yeah. You would.
I like this cable thing you draw out.
Yeah, this is handy, and I'm really glad we're doing it right now in Energy 102 because this skill will serve you very well in ETEC 214, and the skills in ETEC 214 will serve you really well in a variety of problems. I mean, any energy technology problem, you're going to be doing things almost exactly like this. So. Okay, now what we neglected here is that almost without question, all of the heat energy from the wood did not make it into the water. Some of it went out into the air, obviously. And so probably you could at least double, maybe triple that amount in terms of the efficiency of the process. But there we go. Okay, let me take a quick break. I think we've been running here for a while. Yep, almost 40 minutes.